Calculating correlation coefficients is all about staying organized. This particular scenario, that's the theme. We just have to stay organized. Now let's look. Lancaster Fleet Systems produces onboard information systems for law enforcement, fire rescue, and delivery vehicles. Okay, that's good. Now, in a survey, departments were asked to rate 4 best-known patrol car information systems based on, now notice this, 4 features that officers identified as critical to their opinion of such a system. These are the 4 features: good visibility, speed, helpfulness, and bulkiness. Now, wait a minute. Disturbingly, survey results indicate an advantage for Lancaster Fleet did not indicate an advantage for Lancaster Fleet over its competitors. And we have this table of information. Let's take a look at this. Oh, this is our first set of data. A correlation coefficient study always involves marshaling or handling a lot of data. Okay, this is our first table. It is for each one of those features that was just mentioned, giving us a score for, this is essentially 4 different brands, including Lancaster Fleet. Now, that one little phrase that I tripped over did not indicate an advantage. What's going on here, what's being discussed is this is their information system, and you notice that they're not getting super high scores except for bulkiness, which doesn't sound like a good thing in a computer system that's installed inside of a vehicle. Okay, nonetheless, we're still reading the scenario. Oh, wait a minute. Lancaster Fleet's engineering department rated the 4 systems. Oh yeah, see how this is a list of the same brand names? And shared this report. Now, the columns here on the second table are different. Size of screen, size of desktop area, use of color, but again, each of the brands was given a rating. In this scenario, here's the big question. Is there any significant correlation between the feedback from engineering and the feedback from the customer survey? Now, I underlined that in orange ink because we have to remember through all the middle part of this, all of these calculations, we have to remember that that was the question. This is the question that we will ultimately answer. What we have here is 2 different sets of data. You've got 4 brands of information systems. One set of data is what the customers thought. The other set of data is what engineering measured in the system, the size of the screen or the count of the click-throughs in the particular program. We are wondering if there's any correlation between the 2. Oh, that is to say, now wait a minute, correlation. What is correlation? Well, we could actually slip that right in here before we turn the page. Correlation. A measure of the strength of any linear relationship. I don't know, will it fit? Yeah, I think it'll still fit. Of any linear relationship between 2 sets of observations. Sets of observations. And you go, oh, I get it. We have 2 sets of observations here, right? We have these 2 tables. Oh, actually, the bad news is we have many more than 2 sets of observations because, for instance, this column of good visibility, that's considered a set of observations. It's 4 different scores concerning visibility for 4 different information systems. Speed is a set of observations, helpfulness, bulkiness. Oh, wait a minute, and then all of these are so-called sets of observations. And we're asking a question, when you're looking from one table to the other, do we think there's any linear significant relationship between these 2 things? Okay, and there is a way to investigate that. That is the, correlation study, the calculation of correlation coefficients. A single numerical score for the strength of the linear relationship between any column up here and any column down there. Oh, all right. Now, what do we need to do that? Well, if you've got the note frame, the second page contains the formula. We need that formula. Oh no. Correlation coefficients are typically abbreviated as rho or lowercase r, and in order to calculate a correlation coefficient, you have to fill in that whole formula. Oh, wait a minute. You have to fill in the whole formula. It involves a bunch of, right, x's and y's. What are these? These are the two sets of observations. Now, wait a minute. Here, this is a blank table. This is actually our ultimate goal, is to fill this out. Because see here, as the rows, visibility, speed, helpfulness, and then bulkiness, maybe not so much. Those were the four things that the officers were concerned about with the inboard information systems. These columns are engineering's observations: size of screen, use of color, count of click-throughs, autofill activity. Now, why have I bothered to draw in then a grid? Because now that I've drawn a grid, each, whoops, that's crooked. Each empty cell in this grid, for instance, and I'm just picking on one of them, the size of the screen and visibility, right? This particular one right here. Each one of these empty cells in this table needs a correlation coefficient, because each one of these empty squares represents what is it at the intersection of what row and what column, suggests a pair of some certain customer attribute like visibility and some certain measurable engineering specification such as size of the screen. Oh, we want to test if there's a relationship. What do? We fill out that formula up at the top for each and every one of these. Now, you're looking at the formula and thinking, okay, fine, but what is x and what is y? Actually, in this particular setting, you could take your pick. We know that to work on that upper left-hand corner, we need the data for good visibility, right? And we need the data for size of screen. That's right here. We need these two sets of data to work on what goes there. One of them is x, one of them is y. In this particular setting, you could take your pick. Why don't we just say good visibility? That's data set x. The scores for size of screen, that's data set y. Oh, all right, now we're still trying to calculate the correlation coefficient. Remember I said the secret is just stay organized. Take your time and stay organized. Now, the first thing that I recommend is why don't we, since we're only working on that one upper left-hand corner of the table right now, right, we do these one at a time, why don't we pull this data that I have boxed here over to this page? Let's stage it where we can see it better. Because what were those scores? I'm just copying the data from the page before. Visibility. The scores were 5, 3, 1, and 10. Now I don't have to keep. And a little reminder, I said, okay, fine, they'll be x. Now I don't have to keep turning the page back and forth. And then also we need the data for size of screen. Size of screen. And a little reminder to myself, okay, I said that that was y. What were those numbers though actually? 6, 5, 2, and 10. Oh, all right. Okay, fine. Now, I haven't determined anything. I just pulled the data. Now, why did I do that? Because in order to calculate the correlation coefficient, we basically need to find all of the puzzle pieces that fit into that formula. The puzzle pieces, although otherwise known as summary statistics. For instance, what is this supposed to mean? What is this supposed to mean? Well, sigma always means sum or add up. That right there is the sum of x. Oh, that's easy to find. That's easy to find because I said, oh, these observations, they'll be the x's, so to speak. This right here, in the formula, I need the sum of x. The sum of x, you just add those up. So I did that. I added them up, I get 19. Okay, I'm going to record that. We need to kind of store that information. And then the same thing here. We also need sum of y. Well, that's super easy. Just add these up. Sum of y, I get 23. Now, think of it like a scavenger hunt. We found that. We found that. What else do we need? I'm looking at, for instance, in the formula, there's a lowercase n. Lowercase n, it's not just a correlation coefficient. Lowercase n across most formulas and statistics is always signaling the size of the sample. Sample size. How many are you working with here? How many? Well, that would be, let's see, how many information systems did they bother to look at? 4, right? There were 4 brands, n equals 4. N equals 4, got it. I'm just going to note that down. Another puzzle piece that we need in the formula, in the numerator, you see sigma, sum up, x times y. What is that? Oh, well, that's each x multiplied by its y for a particular brand, and then add them all up. Oh, okay. Well, then what would be handy here is to first create a column in which I'm looking at the data. First, I multiply an x times a y, and I just record that. Like 5 times 6 for Lancaster Fleet scores. You know, that's 30. 3 times 5, that's 15. 1 times 2 is 2. Even I can do that. 10 times 10 is 100. Why am I doing that? Because now, these is each x times each y. I want to just add them all up. When I add them all up, I get 147. There. That's the other piece that we need for the numerator. Now we pretty much have everything that we need for the numerator of that big formula. We lack some things for the denominator. For instance, I noticed that right in here, it's the sum of x squared. What this is indicating is that you take each x, like the 5, the 3, the 1, and the 2, take each one, square it, then add them up. Okay, I need that, whatever that is, sum of x squared. So again, be handy just to first create a column in which you square the x's. Okay, so like 5 times 5 is 25. 3 times 3 is 9, 1 times 1 is 1, and 100. 10 times 10 is 100. Add those all up through here. I did that. I got 135. That's that part right there. Got it. Okay, so we have this, that. This is just the sum of x again. Square it. Oh, whoops, and there's one other thing we need here. It says sum of y squared. Roll right, here's the y's. First square them up. Okay, 6 times 6 is 36. 5 times 5 is 25. 2 times 2 is 4. And 10 times 10 is 100. Then add all those up. 165 is what I got. Perfect. 165. Okay, now I have each and every piece that I need for that formula. Some assembly required. Now it's time to actually assemble the correlation coefficient. All right, so this could be kind of like my assembly area right in here. The correlation coefficient between visibility and the size of the screen. Okay, the numerator begins with n. Well, that's 4. N times the sum of x times y. All right, I found that. That's 147. So it's 4 times 147 minus the sum of x, that's 19, times the sum of y, that was 23. That's the numerator. In the denominator, I need to leave plenty of room because it is a big square root in the denominator. Now, what is within the square root? Well, there were square brackets, and then it says n. Okay, that's 4. N times the sum of x squared, that's the 135, minus the sum of x squared. Now that's where you take the original sum of x, 19, and you square it, 19 times 19. So inside this bracket you say 4 times 135 minus 19 times 19. Okay, and when you have that result is multiplied by something that looks pretty similar, but it's just y's. 4 again. times the sum of y squared, ooh, that's the 165, minus the sum of y, just the plain old sum of y, 23 squared. So 4 times 165 minus 23 times 23. Oh, all right, now I did that. You can check me on this. I get the numerator reduces to 151, the denominator to about 153.13. Remember, you have to take the square root of all that once you have found it, so that the whole thing boils down to 0.986. Phew. Okay, we have this number, 0.986. Quick, 0.986. That goes there. We have found the correlation coefficient between the data on visibility and the data on the size of the screen. What's that supposed to mean? Oh, hold on to that thought. Hang on to that thought. The question had just asked about correlation in general. It hadn't asked about that one particular relationship, which means that now we need to repeat this entire process for each and every other pair of X and Y. Oh, he said, great. Now are you going to start right up and do that again for speed and size of the screen? No. No, I'm not going to do the other ones manually. I will give them to you, because we should talk for just a second about, like, well, what are they supposed to mean? I will give them to you, but I will tell you how I actually got them. I have to be comfortable with Excel. In that particular spreadsheet package, here's my secret. It's not really a secret. Title, the formula equals C-O-R-R-E-L. It's the first part of the word correlation. It's a formula, so there's brackets, range of x's, comma, range of y's. All right, so if you've worked it all with Excel, you know ranges selecting, type in the scores that are supposed to be x, type in the scores that are supposed to be y, type the formula equals C-O-R-R-E-L, right? Select the x's, comma, inside the formula, select the y's. Bingo! It is pre-programmed to calculate that, and it will report the answer. Oh, all right, so that's actually where I got the rest of these. Okay, because, first off, let's just finish out the table. If you do that, you discover that the correlation coefficient between visibility and the size of the desktop area, I get negative 0.091. Then visibility and use of color, negative 0.662. Continuing across the top, negative 0.324. And then the last one, visibility and autofill activity, 0.138. All right. Those are the correlation coefficients associated with visibility. What about speed? Okay, in the case of speed, negative 0.349 for its correlation with the size of the screen, negative 0.018 for its correlation with the size of the desktop area, negative 0.298 for use of color, negative 0.659 for it and count of click-throughs, and then 0.761, no negative sign, between speed and autofill activity. Finally, helpfulness, what is it correlated with now? Negative 0.431 is the correlation coefficient between it and size of the screen. Let's see, 0.133 is the next correlation coefficient, then 0.884, then 0.998, then a negative 0.967 finishes out that row. Finally, last row, 0.559, 0.682, negative 0.475, negative 0.547, and then finally 0.265. One last correlation coefficient. All right, we have our so-called relationship matrix. This part right in here. Now, this is great. Are we done? Well, yes and no. We have our relationship matrix. We have done our correlation study between the customer value attributes and the engineering specifications, but we haven't actually answered that question, right, on the page before, the one question that was asked. Because it says, is there any significant correlation between the feedback from engineering and the feedback from the customer survey? This answers that question, but you have to know how to read it. Oh, right, because what are these numbers supposed to mean? Okay, go back to this formula right here. You take this formula, any two sets of data, call one X, call one Y, fill out that formula. You will get back an answer. The two sets of data may or may not have anything to do with each other, but you'll get back a number. That number will be between 1 and -1. That's a thing with this formula. It always results in a number between 1 and -1. Okay, if the number is very close to 1, we say, there's a very strong positive correlation between those two sets of data. When one set of data, the numbers tended to be high. The other set of data, same thing, the numbers tend to be high. They seem to travel with each other. Oh, all right, significant. Now, what would you call significant? Like, how close to 1? Well, this is a little bit of a judgment call. But typically, like these kind of studies, we don't really get interested unless the correlation coefficient, to say it's really significant, like something around 0.8 or higher. Although, you know, if it's like 0.6 or higher, we're still sort of interested. That's sort of correlated. Now, let's just look in the data. Where did that actually occur? The very first one that I did by hand, right here, visibility and the size of the screen, is an example of a very, very strong positive correlation. 0.986, that is very, very close to 1. Notice here also, I'm just looking to spot correlation coefficients that are really close to 1. That one's between helpfulness and the count of the click-throughs, okay. Anywhere else, really, really close to 1, well, no, not exactly. Although this one's pretty strong, it's above 8, right in there. Okay, well, that's helpfulness and the use of color. And this one at least is above 6, bulkiness and the size of the desk area. This one is above 0.6, right? Speed and autofill activity. Oh, all right. Now the only thing I'm doing is highlighting the ones that show strong positive correlation. What's this supposed to mean? Oh, well, look at, for instance, speed and autofill activity. You know, autofill activity is when you type a few characters and the program guesses what you're trying to type and it fills in the rest. Oh, anytime a program used a lot of autofill activity, the score for autofill activity was high, the customer gave it a high score for speediness. And this sort of makes sense. Oh, well, it must actually be helping the customer, the client, work faster. Strong positive correlation. Our very first one that we did by hand, visibility and the size of the screen, that's another excellent example. Oh, okay. When the engineers said that a system had a particularly large screen, you know, high score for size of screen, customers tended to say that same system had good scores for visibility. Okay, oh, the larger the screen, the greater the visibility. Okay, that sort of makes sense, but we've confirmed that relationship. Now, those aren't the only significant correlations, because I said that the correlation coefficient will come out between 1 and -1. If the score that results is really close to 1, that's strong positive. Got that. If the score is close to -1, that is strong correlation. It's strong negative correlation. It just means that the two sets of data definitely look like they're related, but they always move in opposite directions. When one's high, the other one's low, and vice versa. But that's still a significant relationship. So we would want to go through, why don't I pick a contrasting ink color? We would want to go back through this matrix and see if we can spot strong negative correlations. Oh, negative 0.967 doesn't get much stronger than that. Helpfulness and autofill activity. When there was a lot of autofill activity, score was high. The score for healthfulness was low. Oh, that's interesting. All right, what else? Well, there is at least a score below negative 0.6. Visibility and use of color. Okay, so while the size of the screen seems to go with good scores for visibility, it looks like the use of color, a high score for that seems to work against the score for visibility. Interesting. Here's another one right here. I'm just looking for the ones that are below negative 0.6. That one belongs to speed and the count of click-throughs. So those two things it's suggesting tend to work against each other. I think that's spotted all the significant ones, provided that you agree that we define significant as being above 0.6 or below negative 0.6. Again, that's a judgment call. Now, at this point, we concluded the correlation study. We have answered the question if there's any significant correlations, because that's what I was highlighting, the ones that were above or below a certain break point. Any correlation coefficient that's really close to 0, it's suggesting that there doesn't appear to be much of a relationship between two things. For instance, visibility and size of the desktop area, right? Well, the desktop's not what you're looking at, so doesn't look like there's much of a relationship there. At this point, we have actually addressed this question that was asked in the scenario. You might be wondering, well, okay, great. Those are the significant correlations. Now what are we supposed to do with that? Oh, but that is actually the subject of the next scenario.